Welcome. Today I will take you through the steps to control and download data from your Rigol DS1054Z oscilloscope using Python and a Jupyter notebook. This tutorial uses the DS1054Z library written by Philip Klaus. This library is required to replicate these examples in your environment. We'll begin by importing the libraries for the scope, then the Matplotlib libraries, and this one is if we want to adjust those label formats, and our friend Numpy. We're going to grab those image libraries, and finally the SciPy library we need for the spectral analysis we're going to do at the end. With that overhead behind us, we're going to connect to the scope and see if we can get some data to show up on the screen. And this is the IP address for my scope. Of course, you'll need to enter your IP address here. And we want to print this to see what our connection parameters are. Should respond with the make, model, and serial number. Looks like we have, so we have a good connection. Finally, I want to make sure the scope is in run mode so we actually collect some data here. The scope has collected some data. Now I'm going to stop it. Be sure the data that's in the buffer of the scope is the one I want to bring into the Python Jupyter notebook here. So this is the command for the scope library to pull the screen buffer. Actually, it wasn't. That's the command. And this is the command to display that bitmap. All right. So this looks good. What we're looking for here is our horizontal time scaling, vertical axis scaling, and overall the appearance of the data on the screen. We're going to begin preparing for data collection by saving off the vertical scale characteristics. We can get that right from the scope, where this 1 indicates channel 1. So it tells us that it's 0.125 volts per division, and you can see that matches that 125 millivolts up there. The next thing we're going to need is that time scale. And we can get that right from the scope. Unfortunately, there's not a quick command to query this directly, so you have to use a visa command. These are fairly self-explanatory. They're almost English. And the question mark here indicates that it's a query. And then I'll print it out just to be sure I got the value I expected. Okay, and it responds with 0.05, which is 0.05 seconds. That's the equivalent of 50 milliseconds, which is this value that we have up here. So it looks like our scope is responding well. And while we're in this mode of looking at our parameters of the signal itself, let's go ahead and calculate another key feature. We want the sampling frequency. That command, as I mentioned, returned a value of 50 seconds, and that's per division. The scope has a total of 12 horizontal divisions, so the total sample time is 50 milliseconds times 12. That gives us 600 milliseconds. From the scope documentation, we know that there's always going to be 1200 samples in this screenshot. So that's going to let us calculate the sampling frequency by dividing 1200 by our time base by the number of divisions we have. Just doing some quick math, that should work out to about 2000. Okay, that's pretty good. I'm going to scroll down here and give us a little more room to work. One thing I will mention, I don't know how the scope is handling downsampling. Its buffer size, and we'll see that when we get down to the raw, is much larger than 1200. I don't know if there's aliasing correction, aliasing filtering in place or not. So whenever I'm doing any sort of serious analysis, I will always grab the raw waveform, verify my frequency of content is solid in the range I am capturing on the screen, and then use it from that point on. All right, one last bit of record keeping here. We're going to want to keep this identification number. It comes in handy if you have to remember which scope did which measurement, or if you find a problem with a scope and you want to know which data sets are impacted, having this stored is a big help. Finally, the fun part, we get to grab the data itself. So this is going to be channel 1, and the mode is going to be norm, and that's the mode that pulls the data from the screen buffer. Okay. Lastly, I'll put the scope back in run mode so that it continues to run in the background. Before we can plot the data, there's a couple other things we need to do. One of them is to calculate the length of samples, just because that comes up over and over again. And the other thing we need to do is create a time series so we can plot the signal versus time. It always starts at 0, it always goes to 1 less than the number of samples in the data set, since it's 0 based, and there's always same number of samples in this as there are in the signal, and you can divide the number of samples by the sampling frequency, and that's going to give you the delta time. Fantastic. We have everything we need for a plot, so let's set that up. This is going to take a little bit of time, but it's worth it to get the plot in a format that we like. This first command here is going to help us set the aspect ratio and the size of the figure. So this is 16 by 4 inches. It'll fit in this pane just fine. Next, we'll start the figure, and we'll plot our data. So the independent axis is going to be our time, and the vertical axis is going to be the value from the scope itself. We'll go ahead and put the grid on. We'll also go ahead and set up our labels here. Horizontal or x-axis is always going to be seconds. We're going to set up our maximum to be the maximum time it took for that sample. Seems a little bit of an awkward way to do it, but I got started this way. You could also just pull the first and last sample out of the time-based vector as well. The other thing that is nice about this, though, is it does connect the value directly to the scope. We're going to set up the ticks in the plot so that it matches exactly what the ticks and the grid spacing looks like on the scope. So we'll set that up to go from 0 to x max. And the scope does not include the 0 as a division, but Python does. So you actually need 13 of these instead of 12 to get the 12 divisions to match the scope. And we're going to modify that axis so that we have the correct formatting on there as well, so that doesn't screw us up. And we're just going to do 2 decimal places. Finally, the y-axis. And again, this isn't computationally efficient, but this is a nice way to tie the plot features directly into those values we took from the scope above. And we'll put a title on there, and this is a good chance to use our best practices. Bring in that instrument identification number and document our channel. The \n is just the new line character. Finally, we want to show this. It looks like I made a mistake up here. I did. Bad habit. All right. Except for that typo, things went very well, and it looks like we have our time base on here. And just a quick comparison, we want to be sure that we have our 12 divisions. We do. That goes out to 0.6 of a second, or 600 milliseconds. And it looks like our vertical scaling is roughly correct as well, matching what we have up here on the oscilloscope. Next, we're going to take a single-sided spectrum of the data and plot that out so we can get an idea of what that frequency content looks like. This has been covered in a separate video. I'll post a link below. But if you haven't seen that video, that's okay. These are just the commands that we use to calculate that single-sided spectrum. And then the next commands below are what we're going to use to plot it. And I talk a little bit about this in the other video, but you have to scale this, by half the number of samples since this is a single-sided spectrum. And this next command is just going to give us the labels. The labels for the frequency bins, that is. These next lines are going to create that spectrum for us, starting with the figure. So we're going to use our bin labels as our independent. We have to take the absolute of the spectrum because the spectrum always returns complex values. We're only interested in the amplitude in this plot. Phase does have a lot of good information in it, but that's probably a topic for another time. The way we've configured this, our horizontal axis is frequency in units of hertz. I'm going to take the X limit and just focus in on 0 to 100. One thing that I should probably mention is that the best spectral analysis is the one you do with your eyes, looking at that time domain first. And it's real easy to take a look and see there's a periodicity back up here, about every 1/10 of a second. So that tells us that that machine is running 10 times a second, so that's about a 600 RPM machine. This is watching a tachometer on a machine. I probably should have mentioned that. So we're going to want to look at those fundamental harmonics and be sure when we look in that FFT that we have at least one fundamental frequency there at about 600 hertz, and we should see a harmonic because this is anything but a nice pretty sinusoid that we're looking at there. We're also going to want to label our y-axis. We know that's volts because this came right from the oscilloscope. And we're going to put a title on there too. And we'll show that. Yeah, so this is quite an ugly spectrum, but that's what we would expect just because that's quite a complex signal. So our first fundamental is at about 10 hertz. That's this bump right here. And that aligns with what we have up here where it's 600 RPM or 10 hertz. So we look really good there. And because it's complex, it's made up of a lot of other sinusoids, it gives it this jaggedy appearance. And it's actually what we'd expect for a signal like this. So that completes the section on the screen. What I want to do next is take you through the raw waveform and what that looks like to capture. The calculations and some of those are a little bit different. To begin the raw waveform capture, the first thing we're going to do is we're going to stop the scope. Following that same pattern as before, we're going to take care of all those unfun things. Go ahead and get our scales and all that set up, starting with that vertical scale. One thing we are going to do is put a suffix of raw in here to differentiate this from the screen capture up above. We'll print this out so we can see it. That matches what we would expect to see here. So before we calculated the number of samples after we'd acquired the signal, and we did that because we knew we were always going to get 1200, so it's just an easier way to do it than entering it manually. But here we're going to actually acquire the number of samples and sampling frequency directly from the scope itself. So beginning with the sampling frequency, we're going to get that with a Visa query. And the total number of samples that we're going to have is also obtained from a query. This one, fortunately, we don't have to use Visa for. We can use this call here, which gives us the memory depth internal currently shown. And for good practices, we'll go ahead and get the identification number as well. Lastly, but by no means least, we can download the data from the scope. This is going to take some time, so you'll get to see my skills at accelerating video here. And it'll give you an idea of what to expect when you do it yourself. I got impatient the first few times I did this and didn't let it finish. So we're going to change the mode here to raw. And we're going to go ahead and hit that and begin. All right, looks like we're done. Let's verify that we have data in there. Great, so we've got about 6 million samples in there. Just like in the example above, the next thing we're going to do is we're going to set up our time series. This is going to be calculated a little bit differently. We don't have to worry about divisions or any of that thing, since we read that directly from the scope. Do want to make sure that we grab all of these variables with the suffix raw in there, or we'll get garbage results. Put the scope back in run mode, and we'll plot this out. And rather than type all this in, I'm just going to copy and paste from above and change the names to protect the innocent here. So all these have that suffix of raw in. And in this case, because we don't have divisions, we can actually take the last time sample and use that. Do that with the -1. Everything else in here stays the same. And we'll put a designator here so we know this is the raw one we're looking at. And there it is. So very cool, right? 6 million samples came up in half a second here in the Jupyter notebook. It's one of the things I love about Python is it's fast and responsive. It's really fun to use for these larger signals. And you may be a little disappointed if you're looking at this initially and thinking, man, for all that time and work, that waveform down here, this raw one, it doesn't look all that much different from this one up here. And it's true at this scale because we're zoomed out so much. But if you were to zoom in, and we can do that up here, let's say we zoom in to just the first 0.2 of a second. Now let's make it 1/10 of a second. We need to comment out these lines as well. Now we can zoom in, and you can see there's data, granularity that's visible to your eye in these spikes. If I do the same thing down here in this plot, you can see there's a lot more granularity, especially around here where there's a transition in the waveform. Things are a lot smoother. So if you're looking for high resolution data out of the scope, this is the way to go. And as I mentioned before, that's something that I do to check to make sure there's no signal processing as it goes from the buffer to the screen. It's getting in the way of the signal I'm interested in. Lastly, but hopefully the fun part here, is to take that same data and we're going to, instead of look at it in the time domain, look at a single-sided spectrum on this. I'm going to do the same thing. We'll just copy the data from above since the commands are essentially the same. Add that suffix to them and get the data plotted up. And again, this is really important to make sure the suffix gets changed everywhere, including these new variables. Again, that's very cool. That's a single-sided spectrum of a 6 million sample, and it was less than half a second. So we're dealing with some fairly big samples. It's really great the way this works here. Let's take a look at this plot. We want to make sure we have the frequency labels from raw. We have the absolute values. That all looks good. Make sure this is labeled correctly. That seems a little wrong. And you can see what I did wrong. I cautioned you all to use the correct suffix, and doggone if I didn't make that same mistake. It looks a little bit better there. And again, you might be a little disappointed in this if you spent all that time and you were looking for low resolution data. I won't go into it here too much, but what you get out of more samples with the same time interval is you get more samples off to the right. You don't get more samples in this low area here, this low frequency area. So this is what we would expect if you want to see the real power of of a high sample rate, take that X limit, that frequency axis way out. And in a linear plot, there's not much to see here. But if we do it in a semi-log format, so now you can see there's data, and I don't think it's significant, but there is something out here, for example, at 80 kilohertz. Maybe that's an artifact of the transducer I've got making a measurement on the machine, or maybe some sort of electrical artifact. But you get these kind of features that wouldn't be captured with the data we did above. Well, I hope with this was helpful. Look forward to reading your comments, and thank you for the time watching the video.